Hello there, and in this video we're going to do another example of how to conduct a hypothesis test via confidence intervals for the population mean. Let us assume a child is born and let x be the random variable that pertains to the weight of that child, and let us assume that for the sake of this example that the weight of the child is going to be normally distributed with some mean mu and sigma, standard deviation. So if somebody claims that the mean weight of a child is going to be about 3,200 grams, perform a hypothesis test with the probability of committing a type 1 error being 4%. So the main difference between this video and the last is that, namely, the standard deviation of the population is not known. And we're still aiming to estimate mu to sort of see whether we can reject or fail to reject this claim. All right, so let's begin in going through the waves of what we know how to do. So the null hypothesis is that the mean weight is equal to 3,200 grams. And if you do not have any alternative knowledge of this problem, then you probably would be safe of using the alternative hypothesis that mu does not equal to 3,200 grams. And also we're given that the type 1 error must be equal to 0.04%, which is relatively low. That implies the level of confidence that we are going to be operating under is 96. All right, so how do we approach a problem when the standard deviation is not known? So recall. So let's discuss things just a tad bit. So recall that this number zx bar equals to the square root of n times x bar minus mu divided by sigma. This variable is normally distributed according to the standard normal distribution. But we cannot use this because sigma is not known. Therefore, we cannot necessarily use the normal distribution under this case. So there is another conclusion. So one can show actually the number, the square root of n times x bar minus mu divided by s, that this number is actually associated to a t distribution, where nu represents the degrees of freedom. And this is what we call a t-score for the sample mean. So this is pretty much a useful fact that we're going to take advantage of. And here the degrees of freedom is going to be the sample size minus 1. So if sigma is unknown or n is small, then we're going to use a t distribution to find out our confidence interval. And so sigma not being known is obvious, but what about this n is equal to small? So if n is equal to small, that implies that central limit theorem does not hold. So the sampling distribution, the sampling means, is not necessarily symmetric. So the t distribution is going to allow for some, differences in your approximation. All right. So with this being said, let's get back to calculating our confidence interval. So I'm going to draw the typical picture here. So this is going to be some symmetric region, and this symmetric region has some corresponding level of confidence. And this is given to be 0.96. So since alpha is equal to 0.04, then that means this region over here is going to be 0.02, and this is going to be 0.02 as well. And since sigma is not known, this is going to be a t distribution with nu degrees of freedom. All right, so that's going to be that process. So let us assume we gather a sample S. And let us assume this sample has some characteristics here. What do we want it to have? Let's assume we gather a sample, and the sample mean is equal to 3,253 grams. And let us assume the standard deviation of that sample is 22.1 grams. And also let us assume that the sample size is equal to 37. So you go out and get a sample of 37 children, you measure their weight, and you calculate the standard deviation of sample means for these things. All right, so based upon this picture, we know that there exists some numbers t alpha over 2 and minus t alpha over 2 that is going to give us this probability. And again, these are called our critical values. So since the sample size is given to be 37, that means the degrees of freedom is going to be 37 minus 1, or 36. All right, so with that being said, we can proceed with the normal routine. So that means the integral from minus t alpha over 2 to t alpha over 2 under the t distribution with respect to x, this must be equal to 0.96. And if nu is equal to 36, one can find the critical value t alpha over 2 to be equal to about 2.517. And again, if you're not comfortable with the integral approach, you can find this t alpha over 2 value by using the Excel representation t.inv of 1 plus the level of confidence divided by 2, comma, the degrees of freedom. It can give you the same exact number. All right, so once we have our critical values, then we can calculate our marginal error. So our marginal error, if sigma is unknown, or n is small, is going to be equal to t alpha over 2 times the standard deviation of the sample divided by the square root of n. So with all of our data that we've collected, this is going to be 2.517 times the standard deviation of our sample, which was collected to be 22.1, over the square root of the sample size. And one can find that this marginal error is about equal to 9.14. Approximately. So once we have this, then we're pretty much done. So that means our confidence interval for the population mean weight of children born, and this is under a 96% level of confidence, is going to be equal to x bar minus the marginal error and x bar plus the marginal error. And the sample mean was calculated to be 3253 minus 9.14 and 3253 plus 9.14. And that's going to come out to 3243 points. Let's round to one decimal place. Let's say that's 9 and 3262.1, and this is measured in grams. So this is our 96% confidence interval for the population mean weight of children born. All right, so now we can conduct our hypothesis test. So the null hypothesis for this study was that the mean weight was equal to 3,200 grams. And I'm going to call this mu 0. So this number does not belong to this interval, right? Because what we have here in our hands, so here's our confidence interval. So the left number is 3243.9. Over here we have 3262.1 grams. And we have this null hypothesis of 3,200. So that's over here somewhere. So of course that's outside of our confidence interval. So therefore, since hypothesis does not belong to our confidence interval, I'm going to reduce the null hypothesis. And that would be the end of this question. But you also need to be sure that you understand exactly what is going on here. Because they actually could be right. This actually could be a bad sample. We don't know. So you should be able to at least discuss, what's going on here. Because do you really think that the difference between the boundary and this null hypothesis is significantly large? Well, this difference here is only, let's see, 3,200 to 3,243. That's only 43.9 grams of a difference. So if you think that is really, really a large difference, then you probably, or anybody that is looking at the study, is probably, not going to sort of argue with you. But if this number is really, really small, or even if the number or the null hypothesis is really close to the boundaries, either side would have the same discussion. Then you should be at least weary of rejecting or even failing to reject something, especially when you are sort of around your boundaries for your confidence interval. But that, goes towards sort of a subjective argument, whether, this null hypothesis is close or not close, to the boundaries of your confidence interval. But at least be able to discuss, these types of things. So be wary. So be aware of discussions. The null hypothesis close to the boundaries of your confidence. And keyword here is close. Like, what is close? Like, you should have some objective measurement of exactly what close is. And that's pretty much how you go about conducting a hypothesis test for the population mean. But there's some things that are new to this video that I definitely should summarize. So first off, if sigma is known, n is also a subjective word. Some people use 30 as a basis, but it really depends on the application. So if sigma is known and n is large, then you're going to use a critical value, and the marginal error is going to be equal to the critical value times sigma divided by the square root of n. And that's going to be used to construct your confidence interval. And if sigma is and small is a subjective number, some people say less than 30, but it really depends on the application at hand. Then if that is true, then you're going to use a t critical value. So d alpha over 2. Error is going to be equal to that value, and you're going to use a sample standard deviation in place of the standard deviation of the population, and that is going to be used to construct your confidence interval for the population mean. But those are your two cases for confidence intervals, whether n is large, n is small, or sigma is known versus unknown. And that's pretty much how to use hypothesis testing via confidence intervals.